All right, so now we need to review some basic linear algebra. So I'm going to quickly go through all these slides. So you probably have to pause if you, well, because this is very well familiar material, but maybe you will have to pause and think about it a little bit. So if you forgot, or maybe you will have to, I don't know, read Wikipedia or look into your lecture notes in linear algebra. So what is important here is that everything here is true for matrices with coefficients in any field, or with, I don't know, vector spaces over a field, right? So here F can be any field. So we have matrices with coefficients in a field, we have vector spaces, we have dot product, we have subspaces, we have orthogonal complements. So all the stuff is well defined with generic fields. So then we have the sum of two subspaces. Now maybe so here we introduce some useful notation so that J is a matrix of all ones. So M by N matrix of all ones, and O is a matrix of all zeros. Okay, so then we have the dimension of a vector space, well defined over a field, row space of a matrix, column space of a matrix, rank, null space. So all this is defined for matrices with coefficients in any field. Okay, now if we have a subspace of the coordinate space Fn, then, and this is a bit tricky, so it is always true that the dimension of a subspace and its the sum of dimensions of a subspace and its orthogonal complement is n. But in fields of, well, at least in rational numbers and in real numbers, we know that if the dot product of x to itself is 0, then x must be 0. But it's not true in other fields. So here you have an example in the field of characteristic P. You can easily construct an example in complex numbers, right? So if you, I don't know, say 1i, so this vector in complex numbers, if you take the dot product with itself, 1i is going to be 0. So, but still, it is true even in C and in ZP and in all fields that the sum of dimensions of a subspace and its orthogonal complement is always n. This follows from the rank nullity theorem. Okay, then we have the definition of determinant. Again, the definition of determinant makes sense over any field. There is also the construction called permanent. So if you delete signs of permutations from the definition of determinant, then you get the so-called permanent thing. I'm not sure if we really need it. We don't need it for the subsequent stuff about town problems, but maybe it will come handy in some of the questions. Okay, and so one more thing is Gram matrix. So if we have a matrix with real entries, well, it has to be real entries because otherwise there is no such thing as being bigger than or equal to 0, right? But if we work with real matrices, then the determinant of M transpose times M is always bigger than or equal to 0. Actually, it's not just that, it's more than that. So it's true that M transposed times M is positively definite. So it means that all its eigenvalues are non-negative definite. So all its eigenvalues are non-negative. And if rank of M is, precise. Stop. Doesn't really make sense. With yeah, equal. So if rank m is strictly less than n, then it means that the determinant is going to be 0. So some eigenvalues are going to be 0. And if rank m is equal to n, so if rank m is equal to n, then all eigenvalues of the gram matrix are strictly positive. All right, and one more remark is about the van der Monde determinant. Again, I'm sure that you are very well familiar with the concept of van der Monde determinant, but I just want to mention that it makes sense over any field.